Welcome to my projectbazaar.com. Let us discuss about the Hadamard-Coded modulation for visible light communications. Let us discuss about the abstract of the product. So VLC means visible light communication systems using the indoor lighting system to also provide downlink communications require high average optical powers to satisfy the illumination needs. So this can cause high amplitude signals common as higher order modulation schemes to be clipped by the peak power constraints of light emitter diode, that is a LED, and a LED to high signal distortion. So in this paper we introduce a Hadamard-Coded modulation, that is HCM, to achieve the low error probabilities in LED based VLC systems needing high average optical powers. So this technique uses a fast Wallace Hadamard transforms, that is a FWHT, to modulate the data as an alternative modulation technique to orthogonal frequency division multiplexing. So that is OFDM. HCM achieves a better performance for high illumination levels because of its small peak to average power ratio, that is a PAR. So the power efficiency of HCM can be improved by reducing the DC part of the transmitted signals. The resulting so-called DC reduce, so that is a HCM. So DC or HCM is well suited for the environment requires for the dimmer lighting of the process. So in this visible light communication refers to the communication technology which utilizes the visible light sources as a signal transmitter, the air as the transmission medium, and the appropriate photodiodes as a single signal receiving component. So visible light is the form in which electromagnetic radiation, the visible light covers wavelength from 390 nanometer to 750 nanometer. So that is a in terahertz range 400 to 800 terahertz. So VLC is a subset of optical wireless communication technologies. VLC can be used for communications and for computing because light producing devices such as indoor and outdoor lamps, TVs, traffic signs, and commercial displays and cars headlights so are used everywhere in the VLC. So VLC can be used for providing security. So high security is needed to the VLCs. They are specifically used in body sensor network and the personal area networks of the systems. Yeah, let us discuss about the flow diagram of the process. So in the flow diagram of the process, first of all, this is the system model, and then transmission model, channel, and then receiver model. So these are the overall flow diagram process. So in the system model, there are subdivided into three categories. One is a transmission model, channel, and then receiver model. In the transmission channel model, like a HCM encoder, there is a Hadamard-Coded modulation encoder. So there is a giving the input like a random input or given in the data. So next of all, the Hadamard transform is used. Hadamard transform is using the process of HCM encoder. So again, that is converted into the QAM modulation, that is quadrature amplitude modulation. It's converted for the mapping. And then in the transmission side, there is the IFFT, so the inverse Fourier fast Fourier transform. So and then the process is transmitted to the transmission model. So in the transmission model, again the converted to the channel. So the channel means like VLC. So VLC is a visible light communication channel. So here we use a AWGN also. So that is additive white Gaussian noise process. So in this process, the channel is used in this here, and then the channel is converted into back to the receiver model. The receiver model just opposite to the transmission model. So adding the MMSC equalizer. So that is a minimum mean square error equalizer is adding, and then FFT. So that is a fast Fourier transform, and then Hadamard invert transform. So here the Hadamard and transmission model, here we use the Hadamard transform, and the receiver model use the Hadamard inverse transforms. So these are the changes to the receiver model. And then the QAM demodulation. So here we are using QAM modulation, and here we are using the QAM demodulation process. Finally we are getting the data sync. So that is a HCM decoder. So these are the overall process of the HCM encoder and Hadamard transform. Mainly use here Hadamard transform is only. Hadamard transform is like one type of a transform. So here we are using before to the QAM modulation, and then the system model is proceeding for transmission, channel, and the receiver model. So here we are using the IFFT. So the FFT is the process of receiver side, and the equalizer for the adding MMSC equalizer. So that is equaling to the HCM decoder. So finally we are getting the receiver model of this process. So finally getting the adding MMSC equalizer. So in this equalizer, the Hadamard inverse transform is a process of in the receiver model. Finally we get the channel and receiver model. So these are the overall flow diagram of the process. Let us discuss about the running procedure for the product. So click the file and then run. So here so many outputs are displayed related to a flow diagram basis. So first of all, the first graph is, so in this view, here the x-axis is the time and y-axis is the amplitude, and then the pulse shaping to increase the spectral efficiency of the, including the time domain of the wave of rise cosine pulse shaping filters. So in transmission, rectangular pulse requires a large bandwidth and is not spectrally efficient. In order to overcome this problem, we use a sine pulse instead of rectangular ones. So the transmitting of the data, that's alpha is equal to 0 and alpha equal to 5 and alpha s is equal to 1. So we add a DC bias to the signals to make them positive. And in the transmittal pulse are 3 rectangular pulses, so replacing rectangular pulses with the sine pulse reduce the SNR so by 0.83 dB. So in this figure the amplitude is up to 0.22 and 1. So the time domain waveform rise cosine pulse shaping filters is basically nearby the alpha 0 and 1 and 0.5. So pulse shaping to increase the spectral efficiency of the. So here the input signal generation, so the input is randomly selected 0 to 100, so here the 0 to 3.5. so this is the input signal generation of the HCM OFDM block. So here in this figure, alpha is equal to 0.4 and alpha equal to 1 and alpha equal to 0.3 and 0.2 using the MMSE equalizer. So that is a minimum mean square error equalizer of DCR HCM and one tap equalizer of the AC OFDM. So in this figure, the 16 of QAM is a quadrature amplitude modulation, and the interleave of DCR HCM is a DCR is equal to DC reduce of the HCM is a Hadamard-Coded modulation scheme. In the DCR, the equal to OK DCR, that's indicated in blue color, and the green is a OK interleave, that is a DCR HCM. So the 16 QAM is existing work, and these are to the proposed work of the average optical received power. So here the y-axis is BER, so the diameter beta rate. So finally we find the equalization of MMSE equalizer of the DCR HCM, one tap equalizer of the ACO OFDM. So similarly, the same figure of the average optical received power, so that is a BER, so the solid lines of BCR HCM and DRC HCM, ACO OFDM and DCO OFDM of RP OFDM versus the average optical received power. So that is calculated by the black is a existing system and green and blue is a proposed system. So overall, these are the running procedure for the product. Thank you for listening this video.